Greetings everybody. This video will hopefully explain how to calculate what's called the moment of inertia of either a uniform object or a system of individual masses. What is moment of inertia? Well, we use an uppercase I to indicate the moment of inertia. And the moment of inertia, you can think of it as the rotational equivalent of mass. Because when something's rotating, it has what's called a moment of inertia. And the moment of inertia depends upon the axis through which the object is rotating. For example, I could take a uniform rod and pivot it about an axis right through its center. You know, I could hold a ruler. I could hold the center of a ruler between my fingers and rotate it. Or I could hold the edge of the ruler between my fingers and rotate it. Well, those are going to result in two different moments of inertia. So moment of inertia of an object or a system of objects depends on the rotation axis. And it's got units of a kilogram times a meter squared. And there are three ways to calculate the moment of inertia. And first we're going to look at, as in this figure, the moment of inertia I for a set of masses. And in this case, I is given by the sum of the mi Ri squares. Or what is Ri? Well, you know, and again, I means you sum over the masses in the system. In this example we're going to solve, there are three masses. And they're fixed on this massless rod. So in other words, relative to each other, they can't move. And somehow this rod is pivoted so it can rotate about the x-axis as shown here. So this rod can rotate as such. And so this sum is going to go from 1 to 3. And Ri, so M1, you know, R1 would be the distance from M1 to the rotation axis, which in this case is the x-axis. R2 would be the distance from M2 to the rotation axis. M3 would be R3 would be the distance from M3 to the axis. And in this case, the rod, these masses are connected. They're fixed to this massless rod. So in other words, the 4, the 2, and 3, they can't move relative to each other. But the rod itself is free to rotate about the x-axis as shown. And I'm just going to call the masses going from top to bottom M1, M2, and M3. And so for a set of masses, the moment of inertia of that system is the sum over I of the mi Ri squares. And again, this is just going to be M1, M2, M3. So I is the sum of the mi Ri squared. So it's going to be M1 R1 squared plus M2 R2 squared plus M3 R3 squared. Okay, and I'm just going to go, it doesn't matter what order you go to, I'm just going to go top to bottom. M1 is the 4, M2 is the 2, M3 is the 3. So M1 R1 squared. Well, M1 is 4, R1. That's the distance from M1 to the rotation axis. Well, that distance is 3 meters. So this is M1 R1 squared. Okay. M2 R2 squared. Now notice it doesn't matter that M2 is a distance of -2 from the rotation axis because it's squared. You know, moment of inertia can never be negative. But this is my M2 R2 squared. Likewise, what about M3 R3? That's my M3 R3 squared. So nothing complicated. In the brackets you get this sum and you add it up and you get 92 kilogram meter squared. You know, so, and typically when you're talking about the moment of inertia of a system of masses, you know, it's a mass, one or more masses, and they rotate relative to an axis. And the distance Ri, that's the distance from the mi to the rotation axis. So for a single mass, relative to a distance r from a rotation axis, for a single mass, the moment of inertia, we call it mr squared. Where r, by definition, it's not a radius. It's the distance from the mass to the rotation axis or to the pivot point. So M1 is a distance of 3. You know, everything's in MKS. M1 is a distance of 3 from the axis, or distance of 3 from the pivot. M2 is a distance of -2 from the pivot, but it's squared anyway, so it doesn't matter. M3 is a distance of -4 from the pivot, or -4 from the axis. But it's the MI/RI squared. So for one mass free to rotate relative to a pivot, I would be mr squared. Now, more complicated is the moment of inertia of uniform rigid objects. Well, for those, you just look them up in the table, which I provided here. Now, the one thing to be careful about is, again, moment of inertia depends on the rotation axis. Now, when we talk about ICM for and again, when we say uniform rigid objects, these are particular examples here. Uniform again, or homogeneous, meaning the mass is distributed uniformly. Here we've got a hoop or thin cylindrical shell, solid cylinder, a hollow cylinder, meaning it has an inner radius of R1 and an outer radius of R2. Here's a uniform rod pivoted about an axis through its center. Same uniform rod pivoted about an axis through one end. Here's a rectangular plate, also known as a lamina. Here's a solid sphere. Here's a hollow sphere, i.e. a spherical shell. In each case, the mass of the object is large M. In each case, the radius is large R, where it's R1, R2, large R. Here, the length of the rod is L. Here, this is the rectangular plate pivoted about an axis through its center. The sides of the plate are short side A, long side B. And ICM means that the rotation, the pivot, it's pivoted through the CM. So here, notice, and again, you can see the rotation axis is given by this line, and the arrow indicates so this is an ICM, ICM, ICM. This is an ICM. This is not. In this example here, the rod is pivoted about one end. This is an ICM. The lamina is pivoted about an axis passing through the CM. Here, the solid sphere pivoted about an axis through the CM. Hollow sphere pivoted about an axis through the CM. That's what we mean when we say ICM. The rotation axis passes through the CM of the uniform object. So for a cylindrical shell or hoop, ICM is mr squared. Cylinder, solid cylinder, ICM 1/2 mr squared. Hollow cylinder, that's on the final. ICM is 1/2 m, parentheses R1 squared plus R2 squared. Uniform rod pivot about the CM, i.e. through its center. 1/12, where the length of the rod is L. 1/12 ml squared. Rod pivot about one end, I is 1/3 ml squared. For the lamina, ICM is 1/12 m, parentheses A squared plus B squared. Solid sphere through the CM, ICM is 2/5 mr squared. Hollow sphere, ICM is 2/3 mr squared. And those are the most common uniform objects. And homogeneous is the same as uniform, meaning the mass is distributed uniformly throughout the object. So for the ICMs and for the special case of the uniform rod pivoted about one end, just look them up in this table. And they have units of kilogram meter squared. Now, in the next lecture, well, Dr. Gomez, I pose this question. What if the object is not pivoted through the CM, as in the second example of the uniform rod? How do we know that a uniform rod pivoted about one end? How do I know that the I is 1/3 ml squared? Well, there's something called the parallel axis theorem, which we'll cover in the next lecture. But for now, to get the moment of inertia for uniform rigid objects pivoted about an axis that passes through the CM, for the rotation axis that passes through the CM, or they give you the other one with the rod, just look them up. Where large M is the mass of the object. If the object has a radius, large R is the radius, large L is the length. And that's it. So now, what about again? What if I have an object? Here's just some randomly shaped object, but here's the axis through the CM indicated by the red X. Well, what if it's pivoted about an axis that passes through some other point on the object. What is the moment of inertia if it's pivoted about this axis and not this one? Well, that's something called the parallel axis theorem. That'll be the next video. But again, uniform rigid objects, hey, look them up in the table. Again, assuming that, except for the rod, assuming that the rotation axis is through the CM, which is every case except this one right here. Okay, let me get this video saved and posted.